Hi everyone, my name is Deepak and my project is BuzzTrace, the integration of infrastructure monitoring and distributed tracing tools with Georgia Tech's BuzzBlog application. This presentation will involve a quick recap of the motivation behind this project, a brush up the concepts pertaining to monitoring and tracing, and with the relevant system architectures, I'll then move on to project milestones as described in the follow-up reports, with each milestone accompanying a demo. One point to note is that all the videos present in the slide deck were created on my local system and recorded using a screen recorder. A bit about myself. I'm a CS grad student at Georgia Tech with a computing system specialization, and I have 3 years of industry experience building scalable SaaS products as a data engineer. I have used containers and orchestrators extensively and had a brief exposure to infrastructure monitoring and distributed tracing as well. So the motivation behind this project was that most software companies in 2000s had tech stacks that look like this, right? Whereas tech stacks of modern applications look more like this. As you can see, it's a much more diverse, distributed, service-oriented architecture with loosely coupled components. It's like polyglot in nature with different stakeholders maintaining different services, which could change over time, right? Moreover, it's expected to run on an array of different hardware infrastructures ranging from cloud providers, developer machines, QA environments to air-gapped on-prem environments with strict regulations, right? And the industry also witnessed some very architectural and business-oriented trends like the progression towards microservices, the emergence of cloud providers offering infrastructure as a service for dirt cheap prices by leveraging economies of scale, and as it has always been the triumph of open source software. And there's really no prices for kissing the developer in the bottom right corner, working on his desk setup. Yeah, as software systems became complex, uh, observability became an important aspect of software architecture right from its inception, right? In fact, there is no point in deploying an application that scales from 10 microservices to 100 microservices based on, 10 instances to 100 container instances based on user traffic if one has no way to measure the said traffic. An even more disastrous situation is when you have hundreds of microservices running. 100 is like a plausible number these days, even for small startups. And there are no observability tools that can actually detect an alert based on the health of these microservices. So it became notoriously hard to manually ensure that the entire system composed of all those ephemeral services is actually up and healthy. This is where observability comes in. And the popular book Distributed Systems Observability by Cindy Sridharan concludes that the three pillars of observability are logging, infrastructure monitoring, and tracing. This project will focus on the latter two by integrating them onto BuzzBlog. This slide is a quick primer on monitoring. In this project, I'll be exploring and using an open source monitoring tool named Prometheus, whose system architecture is in the top right corner. Right, Prometheus is one of the first monitoring software that follows a pull-based metric aggregation model with enabled service discovery, which is suited for dynamic cloud workloads and Kubernetes. It was a fork of BorgMon, which is an internal monitoring tool used by Google and is currently maintained by SoundCloud. I hope the Kubernetes meme in the slide was funny. Yeah. This slide is a quick primer on tracing. Debugging software that runs as part of an HTTP request response cycle can be hard. And the process of inspecting software with an aim to identify degradation and performance by dividing the life cycle of an event to smaller units called traces is called tracing. And when the event being traced passes through multiple nodes, the process becomes more complex, and it's termed as distributed tracing, right? In this project, I'll be exploring and using an open source distributed tracing tool called Zipkin. It's a tool that's developed at Twitter that helps gather timing data needed to troubleshoot latency problems in degrading microservices setups. As mentioned in the project proposal, the project aims to integrate BuzzBlog with Prometheus and Zipkin and recreate scenarios leading to resource spikes or performance degradations. The architecture of BuzzBlog consists of several microservices pertaining to accounts, likes, posts, trends, followers, etc. And the application is built using using a Flask API gateway, RPC calls using C++ and Apache Thrift, with the entire system being packaged as Docker containers. This slide is a recap of the system architecture that's present in the report and the proposal. Moving on. The first milestone is basically setting up BuzzBlog locally and understanding the thrift message format, C++ RPC calls, and the routing functionality of the API gateway. Since BuzzBlog is an amalgamation of like 15 microservices, it helps to invest some time upfront to make sure that the containers can be orchestrated easily and spawn a subset of them when needed. As you can see, this is the BuzzBlog application that's locally set up by cloning Git. And this is a manual.md file that consists of all the information to run all the microservices. And there are like at least 6 microservices, and then there are other dependent services like Postgres, Redis, API Gateway, etc. Running all of them locally is actually a very tedious job, especially given the fact that when you're testing code or when you're modifying any code and testing it out, every API request will actually expect at least some of these microservices to be running, right? So it made sense for me to first invest some time into creating a Docker Compose setup that allows me to orchestrate a subset of these services at once and specifying all of them under a common Docker network with relevant Docker volumes being mounted, right? Using this setup, I was able to run all the all the Docker containers over here. As you can see, there are close to 16 containers running on my laptop right now, and I could list down all the processes. Most of these are the business use cases that we have, basically our BuzzBlog microservices. Now I can go to Postman and actually test these out. I can hit these microservices and it's actually getting routed to my local host. The next milestone is to integrate Prometheus and enable scraping real-time metrics. By assessing the architecture of Prometheus, one can actually observe a clear trend involving the separation of concerns and evolving complexities. The logos in the right represent a transition of once popular infrastructure tools like Nagios, Nagios being the first one, originating in the 1990s, leading up to the current tools like Prometheus. The transition progresses from basic architectures involving metrics like periodic health checks being fed into the system with the capability to check for missing health checks, to modern systems like Prometheus that offer real-time pull-based scraping of metrics, integration of efficient time series data stores to query those metrics, invention of a query language called PromQL to work on the said data store, allowing external integrations for a dashboarding tool instead of shipping it inbuilt, and offering alerts as a pluggable component. Do refer to the meta skills learning section of the report for more details. Since the team who built Prometheus kind of anticipated the wide variety of targets that it would need to monitor, they chose a design principle that decouples the process of metric extraction away from the central server responsible for periodically collecting those metrics. This allowed them to ship pluggable components called exporters that run as sidecars and can scrape health-based metrics from their targets either using a TCP UDP port or a log file. This architectural decision, coupled with a strong open source community backed by CNCF, led to a massive adoption. And there are over 100 official Prometheus exporters today. In fact, there is an exporter for Minecraft that helps monitor frame rate. Hence, we'll be incorporating the open source exporters for all the dependent components used in BuzzBlog. The links to these exporters are given in the slide. For those scenarios where we need to monitor metrics that are fine-grained to the business logic of our application, we can in fact use the client libraries of Prometheus and enable custom code integration. Let's jump into the demo. Now let's take a look at how we have integrated Prometheus into our system. So the main component is a Prometheus web server whose responsibility it is to scrape uh, metrics from the sidecar containers that are run as exporters. And here are the exporters that we have. We have the node exporter, which fetches metrics pertaining to the compute node on which our application is running on. And we have the Postgres exporter and the Redis exporter. The Flask exporter, however, cannot be run as a sidecar because it requires custom instrumentation into the code base. So we use some GUnicorn libraries to actually instrument it into the API gateway service. Now let's take a look at the Prometheus.yaml config. So this configuration consists of all the scrape jobs which we instruct Prometheus to do. And as you can see, these are the exporter targets. They're actually fully qualified domain names. They're resolved by Docker Compose because these containers are actually within the same Docker network. If you've observed something recursive, if you look at it, there is Prometheus config itself within the scrape config. So what it means is that Prometheus can actually scrape itself and hence monitor itself. So if you look at the Prometheus web server, so this is a web server UI for Prometheus. And if you go to Metrics Explorer, you can actually see a bunch of these metrics that are being scraped by Prometheus. You can actually select any of them and execute them as PromQL statements. Now that the metrics are scraped and ingested into a time series database, we can actually query them using PromQL and create interactive dashboards that monitor these metrics using a tool like Grafana. The initial versions of a lot of these tools came with basic querying capabilities, but over time, dashboarding became a decoupled component with a number of these tools, dashboarding tools focused on certain use cases. For example, Redash and Metabase are very popular open source generic dashboarding tools, whereas Kibana is a dashboarding tool with good support for text-based fuzzy searches across logs, making it a core component of the ELK stack. And for our purpose, we'll be using Grafana since it has good support for generating time series visualization. Let's jump into the demo. Now let's take a look at how we integrate a dashboarding tool to visualize these metrics, right? If you go to prometheus.yaml config, we have a remote write section below the scrape config, which actually instructs Prometheus to export all the Prometheus metrics into Grafana Cloud using my username and API key. And this is my Grafana Cloud account. Grafana Cloud is basically a free hosted solution for Grafana dashboards. If you go to dashboards, you can see a couple of dashboards for each of the exporter that I'm scraping. Let's go to node exporter. This dashboard basically consists of all the information pertaining to my node. So there is a labyrinth of information over here with probably 15-20 panels across, and each one of these panel like this, basic CPU and memory usage panels, right? Each one of them are actually running PromQL commands. So if you look at this is a PromQL statements that that are working on the data that was exported by the node exporter, and they're like highly configurable. You could add labels, you can drag and drop them, you can change the type of visualization, etc. In fact, because Prometheus has a standardized format for its exporters, people actually share these dashboards across. Now let's do something cool. Let's actually try to break one of our services. So I'm going to hit the create command API using Apache Bench tool. So what this does is that it will spawn 50 requests with 10 concurrent requests, all to our API gateway, trying to fetch all the account information that we have. And I'm running all my microservices over here using Docker Compose. So let's do that. Oops. I think I messed up the code. Yeah. So it's benchmarking the application. Now let's go to Postgres and let's see for the last 5 minutes. So you should see a drastic jump in these metrics like average memory usage, transactions, fetch data, return data, etc. In fact, without even looking at the application, by just using Apache Bench to overload our application, we can actually conclude that there is a strong correlation between the number of transactions in one of these services. I'll show that to you in some time. There was a timeout. Basically, our application kind of crashed when I tried doing this. Go to Postman. Yeah, the retrieve account is working, but this API is kind of overloaded thanks to the Apache Bench tool. And let me go back to Grafana. Yeah, if you look at this, there was a huge spike in the number of transactions corresponding to account commits, unique pair commits. And similarly, there is a steady increase in average memory consumption, but it will take some time to actually come up. And if we monitor it for some more time, we can actually see some of these graphs spiking. The last milestone is to integrate distributed tracing into our application to get a holistic view of the entire path traversed by a request as it traverses through different microservices, as given in the slide. This section focuses on the hurdles faced while I try to desperately integrate Zipkin into BuzzBlog. The first hurdle was that Zipkin did not have well-maintained C++ instrumentation libraries. Since BuzzBlog uses C++ RPC calls to pass thrift-based messages, I encountered a lot of versioning and dependency issues while trying to link Zipkin C++ libraries with my BuzzBlog code. I tried using 4 different C++ instrumentation clients, but was unsuccessful in each one of them. The first one being the CPP-kin SDK, which relied on a couple of third-party libraries, which threw a lot of errors while trying to link with BuzzBlog, as seen in the screen capture. Yeah, I'm basically trying to build the account service Docker container, and it's throwing me some third-party library issues, and that gave a huge error trace based on some log file, a log formatting that they were using. Full disclaimer: I'm far from being an expert in C++, and the next library I tried was a Zipkin CPP library, integrating which I ran into a compilation error due to a conflict that seems to be ignored since 2007. And finally, I tried an unofficial Zipkin C++ library maintained by a popular developer on GitHub. But I was again not able to build the project as a CMake file through a lot of build errors. So if you look at it, if you look at this, I'm inside the container, cloning the Git repository and creating a build directory using the mkdir command. And I'm copying the instructions given in the GitHub repository to actually just build it using CMake. But CMake gives a lot of errors when trying to do it. And after failing to integrate the previous Zipkin CPP libraries, I tried integrating a CPP client library of Jaeger, which is another open source tool and a competitor of Zipkin. But it turns out, as in the screen capture, it turns out that C++ Jaeger client is deprecated as it's being refactored to support a new standard named Open Tracing to make all tracing applications interoperable. And finally, as a developer in 2023, I did try to use the last trick up my sleeve, which was to check if ChatGPT can solve the problem. And I gave it the problem of integrating C++ libraries of specific versions with BuzzBlog, but I observed that ChatGPT, although produces flawless code, it really struggles if given a lot of conditions, as it hasn't kept up with any updates post 2021. For example, ChatGPT can definitely write C++ code that creates traces and spans in our code base, but it was not yet able to solve problems like integrating a specific version of a CPP client library onto an existing code base by resolving dependency issues such that the library can uh, work with the transport mechanism like RPC instead of HTTP, and also a storage format that relies on a specific version of Apache Thrift. Moreover, it was not able to write code that propagates trace and span IDs over RPC, although it was able to do that with HTTP. We'll give this a try definitely once they integrate this into an IDE that allows a lot more code to be refactored by AI with ease. As you can see in this ChatGPT in this picture clearly recommends a Python script that has a syntax error. Finally, I was able to use a SaaS product named Datadog, which had excellent C++ support and is rated as the most popular monitoring software in the world, with a market cap of close to 21 billion US dollars. SaaS Hub, in fact, rates its popularity votes to be very high in the categories mentioned in the slide. Let's jump into the demo. I promise you this is my last demo, and here I'm going to take you through the tracing setup which we have integrated, which is basically Datadog. As you can see, I made changes in the account service Docker file to actually integrate Datadog, and I'm linking the Datadog Open Tracing CPP library alongside our source code. So this change has been made across all microservices. And in API Gateway as well, there is some custom instrumentation from Datadog to run the agent that's going on. And in account server, we are actually creating these spans and traces and then also tagging certain attributes of an account. For example, username, first name, and last name. And now let's go to the Datadog dashboard. This is my Datadog account, and this is a tracing dashboard where you could see all the requests that are coming in. As of now, it's just a bunch of 404s. So let me create an account by running some test cases. So I'm hitting the create account API, and it has now created a bunch of accounts. Yeah. So let me just refresh this. I could have refreshed it over here. Yeah. Now you can see new traces coming up, which is basically the post account API. And creation of an account again calls certain other you know RPC calls. So we also have follow APIs and like APIs coming up. So if you go into the post account API, you can see some spans that are basically at the Flask level. So so these are spans where Flask dispatches these requests across different stages, and each of these stages have the latency clearly numbered. And if you go to our custom span, which is create account, you can actually see the account that was created. These are basically the annotations that which we had added previously, right? And there's one caveat is that we don't get a very good looking flame graph that actually can correlate all across these different RPC calls. And the reason for that was that we were using a thrift service called buffered. Sorry, we were using a thrift transport called buffered transport to relay our RPC calls. And getting a unified trace ID passing across RPC calls is actually a tedious effort, and it requires a considerable amount of refactoring to change that thrift service from buffered transport to something else. It's not. I mean, it's not as simple as actually just passing trace information in the headers of HTTP calls just because we were using RPC calls in our C++ code. So that's one of the reasons why we don't see a very good looking flame graph and we just get some Flask metrics. But with enough effort, we can actually integrate that as well. Although that's kind of beyond the scope of this project. And so that's basically our integration. And one of the things to note here is that as developers, we would always prefer open source software. But sometimes open source softwares, especially those some SDKs like C++ integrations might not be maintained properly, and that's the reason why there's always a huge market share for SaaS products like Datadog as well. Yeah. Thanks a lot for listening. Overall, understanding the functionality of these systems and integrating them as a POC onto BuzzBlog was a great learning and trend recognition experience. Please connect with me on LinkedIn and do keep in touch.